Okay, chapter 3, the second derivative test. So remember the first derivative test. This is what you used in your quiz. If the first derivative switches from positive to negative, a relative maximum may occur at this critical number. If the first derivative switches from negative to positive, a possible relative minimum would occur at that critical number, and no change in sign means no extrema occurs. So no relative max, no relative min. So recall, critical numbers occur when the derivative equals 0 or when the derivative does not exist. And to determine where the relative extrema occurs, remember extrema are y values, so we take the critical number and plug it back into the original function. I should make these x's. Okay, so today we'll look at the second derivative test, which is another test used to determine the relative extrema of a function. So either a relative maximum or a relative minimum. So a turning point on the graph of the function. So take a minute, pause the slide if you haven't printed it. Let f be a function such that the first derivative is equal to 0, and this condition has to be met. And the reason for that, we look specifically where a horizontal tangent line would occur. So a horizontal tangent line would occur at x is equal to c. So that's the first condition. And the second derivative has to exist on the interval containing the value c. And that's another reason this has to be met. If the first derivative doesn't exist at c, the second derivative wouldn't exist there either. Okay, so the theorem says if the second derivative is positive, a relative minimum occurs at that point. So the value is c, and then to get what the relative minimum is, we plug that value back into the function. So think about what the second derivative tells us about the function. It gives us information about the concavity. If the second derivative is positive, then our function is concave up. So putting these two pieces of information together, the derivative equals 0 at the turning point. All right, a horizontal tangent line would exist on the function. If my function is concave up, then it verifies this point where the derivative was equal to 0 would be a relative minimum. If the second derivative is negative, a relative maximum would occur at the turning point. Using the same reasoning, second derivative negative tells us our function's concave down. So at the point where the derivative equals 0, a relative maximum would be the extrema there. If the second derivative equals 0, the test fails, so go back to the first derivative. If the second derivative is 0, it doesn't mean an extrema doesn't occur. You just have to use a different method to attempt to make a determination. So again, a relative extrema may or may not occur. Alright, so use the second derivative test to determine any relative extrema. So first derivative, negative 4x cubed plus 12x squared plus 16x. So first step, we have to find where the first derivative equals 0. So if we take out a negative 4x, we're left with the polynomial x squared minus 3x equals 0. Factoring this, x minus 4, x plus 1. So we get 3 values where the derivative equals 0. Alright, so our second step, find the second derivative. So go back to the expanded form. Don't use the factored form to find the derivative. Negative 12x squared plus 24x plus 16. Okay, so remember what the theorem says. Find the values where the derivative equals 0. Then plug those values into the second derivative. If the second derivative is positive, our function's concave up, so there would be a relative minimum at the value of c. If the second derivative is negative, function is concave down, so there would be a relative maximum at the value of c. So plugging these three values in, the second derivative at 0 is equal to 16. 16 is obviously a positive value. Therefore, a relative minimum occurs at the point 0. Now, where does this come from? Plug 0 back into the original. So relative minimum at 0, 0. When I plug 4 into the second derivative, so I would get negative 12 times 16 plus 24 times 4 plus 16. This would be a negative value. So I'd have a relative maximum at 4, and plugging 4 back into the original function, you can verify you would get a y value of 120. And then the second derivative at negative 1 would be negative 12 times 1 minus 24 plus 16. So again, this is a negative value. So another relative maximum would occur at negative 1, and plugging that back into the original, negative 1, 3. So the relative extrema occur on the graph of the original function. Okay. So first step, start with the derivative. First derivative using quotient rule, bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. So using, if the first condition is that the first derivative has to equal 0, the first derivative will never equal 0. Therefore, the second derivative test fails. And that's it. Okay, first derivative using chain, negative 1/2 power times 2x. These cancel. We get x over the square root of x squared plus 1. So where does the derivative equal 0? When the numerator is 0. Okay, so now find the second derivative. Again, quotient rule. Bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. Alright, so these 2's cancel. I'm going to factor out an x squared plus 1 to the negative 1/2. From here, that leaves me with just x squared plus 1 minus x squared. All over x squared plus 1. These cancel, and when I bring the negative exponent to the bottom and add the exponents together, I get to the positive 3/2 power. So we take our critical number where the derivative equals 0. When I plug 0 into the second derivative, I would get a positive value. Therefore, a relative minimum occurs at the point 0, 1. Okay, again, because f of 0 would be the square root of 1. Okay, first derivative, 2 cosine x. Using chain rule for this, negative sine of 2x times 2. So my derivative would be 2 cosine x minus 2 sine 2x. Okay, now to find where the derivative equals 0, I'm going to use sine of 2x would be sine of x plus x, and then our rule for that, sine of the first, cosine of the second, keep the operation the same, cosine of the second, sine of the first. So this combines to 2 cosine x sine x. And I'm going to do that so I can factor my derivative. So I have 2 cosine x minus 4 cosine x sine x. Factoring out a 2 cosine x, I'm left with 1 minus 2 sine x. Now finding where the derivative equals 0. Okay, so cosine equals 0 at pi over 2 and 3 pi over 2. Sine x equals positive half at pi over 6, 5 pi over 6, because we're looking on the interval from 0 to 2 pi. Okay, so for homework, what I would like you to do, find the second derivative, and then use the second derivative test to identify any extrema. So once you find the second derivative, you have 4 critical values to plug into the second derivative and draw a conclusion about. Prepare that for class tomorrow.